So this video is on something called the Triangle Proportionality Theorem. And to get us started, go ahead and just take a look at all of this and what are some things that you notice and some things that you might wonder. Okay, so hopefully you've had some time to think about that. I think these kind of look like candy corn, so I put a little candy corn on here. Some things you might notice are that we've got parallel lines, maybe some similar triangles happening. So some things you might wonder are they parallel? Are they similar? Why do they look like candy corns? I don't know. Before we get into this, I want to refute just a few symbols. Remember, if you have lines like this, it means that they're congruent. Like these sides are congruent and these angles are congruent. If you ever, instead of a little dash, have arrows, that actually means that the sides are parallel. So these two are parallel, and these two that have two arrows are parallel. Or like these are parallel, and all three of these are parallel because they have the same mark. So arrow means parallel, just a dash means congruent. All right, I want to remind you of something you learned probably in 8th grade, which is when you have two parallel lines, if a line ever cuts through those parallel lines, we call it a transversal. That just means literally a line that cuts across parallel lines. It transverses the lines. Anyway, it creates a lot of congruent angles. So do you remember which ones? 1 and 3 are vertical angles, so those are definitely congruent. And then 3 and 5 are what we call alternate interior angles. Actually, we'll review this later, but these are the same. And then 5 and 7 are also vertical angles, so those are the same. We call these alternate interior and these alternate exterior. And then these two that are in kind of the same position, just on the different line, we call those corresponding angles. They kind of correspond to each other. All of those are congruent, and all of these are the same. All of these 4 are congruent as well. Okay, so we're going to use that. Oh, let's go ahead and go through it real quick. So these that are in the same position, or these, or these, or these, those are called corresponding angles, and they are always congruent. If they're opposite each other on the inside, we call them alternate, because they're alternating. Interior, because they're on the inside. Angles, those are also congruent. If we've got on the outside here, those are alternate but exterior angles. Those are congruent. And then, like we've mentioned before, you've got vertical angles that are across from each other. So these two are congruent, and these two are congruent. Okay, so back to the Triangle Proportionality Theorem. This theorem says if you have a line parallel to one side of a triangle that divides the other two sides, a line parallel to one side of a triangle is going to divide the two sides proportionally. So here's what that means. If I have this big triangle and I cut across it with a parallel line, parallel to this side here, first of all, it creates two similar triangles. We know that because if you were to basically dilate out from this point and grow this triangle into this one, it would be a similar triangle. And you would know because if you connected the image to the pre-image, it would go through the center of dilation and connect this image point to that pre-image point. It would go through the center of dilation, and it forms kind of these triangles here. And we've talked about how when you dilate, it always is parallel, these line segments. So anyway, these parallel lines form two similar triangles, and not only that, but it divides the other two sides proportionally, meaning let's call this X and Y, and let's call this W and Z. I know that, well, I already know since they're similar triangles that the little side to the big side is equal to this little side to this big side. But beyond that, I actually know that just plain old x to y is equal to w to z. I can basically like chop up these two segments and they equal each other. That always happens as long as this is parallel to this. Let me show you some examples of that first of all. So for example, if I wanted to find little x here, I've got everything I need already. Since these lines are parallel, I know that the triangle proportionality theorem applies, which says that these are proportional to this. Like this segment cuts this into two proportional pieces. So like 6 to 2 is the same as 9 to x. Or you could have said 2 to 6 and x to 9, either way. Or you could even do 2 to x and 6 to 9. So cross multiply, 2 times 9 is 18 equals 6x, divide by 6, and we get 3. Does that make sense? Seems like that could be a 3, sure. Okay. Here's another example. We're kind of going to work backwards on this one. Are segments MN and PQ, so MN and PQ, are they parallel? They sure look like it, but the way we can tell is basically do what we just did. Set up these ratios, and if those are proportional, then yes, they're parallel. If that proportion doesn't work out, then no. So basically do 42 to 54 and see if that equals 36 to 48. So I'm going to type those in my calculator real quick. So 42 divided by 54 is 0.7, repeating. 36 divided by 48 is 0.75. Are those the same ratio? No, they're just a little bit off. So those are not equal to each other. Therefore, since this ratio is not the same as this ratio, these lines are not parallel. They're pretty close, but they are not parallel. Okay, so you're going to use that to answer a few problems, but I actually want to take you through a proof of this triangle proportionality theorem. So this proof is kind of like the one we did for the Pythagorean theorem, in that we're going to use similar triangles to help us out here. So, let me see. I think the Pythagorean theorem proof's a little harder, and I don't need you to memorize this, I just want to show you so that you're familiar with it. Let's start off with a triangle. I'm going to call this triangle GKI, and I'm going to cut across it with a parallel line. So I'm going to draw the arrows so that it's parallel, and we've got H, and we've got J. And so what I'm starting off with is the fact that GK, segment GK, is parallel to HJ. Just by the way, there's a symbol for is parallel to. It's literally two parallel lines. Those two parallel lines there mean is parallel. So this is parallel to this. So that is given. I'm starting with that. And this is basically going to be like a 2-column proof, where I'm writing like something and the reason for it. Okay, I know that this angle is congruent to this one, and this angle is congruent to this one. So I'm going to go ahead and write that out. So I know angle HGK is congruent to angle IHJ, and I know angle IKG is congruent to IJH. Again, I'm just saying that, but in symbols. How do I know that? Well, I know that because if I have two parallel lines with a line cutting through it, which is what's happening here, this is the transversal, then this is in the same position as this. It's like these two right here. And if you remember the review we just did, those are corresponding angles. I spelled corresponding right? Yeah. They are corresponding angles, and so that's the justification for that. Next, I know that triangle GIK is similar to HIJ, triangle HIJ. How do I know that? Remember, if you're going to say they're similar, you have to use one of the three properties, either angle-angle, side-side-side, or side-angle-side. In this case, it would be angle-angle. I have a pair of angles here and a pair of angles here, so the reason I know this is because of the angle-angle similarity postulate. Postulate just means theorem or property. Okay, next, since I know they're similar, I can set up a ratio of the sides. So I know that IG compared to IH, so IG is the big triangle, IH is the small triangle. I know that that's equal to IK over IJ. Just setting up a proportion with the sides, since they're similar triangles. And that's because the corresponding sides of similar triangles are proportional. So I'm going to write that. The corresponding sides of similar triangles are proportional. Okay. Next, instead of IG, I'm going to replace it with, see how IG is this big segment, and it's actually the same as this plus this. So I'm going to split up IG into HG plus IH, because HG and IH make up IG. Leave IH on the bottom. I'm going to do the same thing with this one. Instead of IK, I'm going to split it up into this and this. So I'm going to make that JK plus IJ. Leave this IJ in the bottom. The reason I was allowed to do this is because of the segment addition postulate. Basically, segment addition. Like, I can add this segment and get this segment. All right, we're almost done. So watch this. The reason I did that whole split up thing is because now I have HG over IH, so HG over IH, and IH over IH. Although, what is IH over IH? Or anything divided by itself? That's just a 1. Same thing here. I have JK over IJ, but when I do IJ over IJ, that's just a 1. And so I could subtract 1 from both sides, and it would cancel and just leave me this. It would just leave me HG over IH equals JK over IJ. The reason for that is just the subtraction property. I'm just subtracting 1 from both sides. It's the subtraction property of equality. And I'm actually done, because look what I have now. I've got HG, so this, over IH, this, equals JK over IJ. So now I have that this over this equals this over this, which is what I was trying to prove. That is the triangle proportionality theorem. If you start with parallel lines, you end up cutting this into proportional segments.